Number 36 in the linked outline involves the kinds of ratios you get from different proportionalities. For example, if y equals kx cubed, and we have data points x1 and y1, the proportionality is going to read y1 equals kx1 cubed, where x1 and y1 we assume are known numbers. We can solve then for k. K is just going to equal y1 over x1 cubed, and then we plug this number in for k and we have the proportionality. Now that isn't what I said it was. That's just how we find the proportionality constant given the proportionality in a data point. Number 37 concerns how we fit power functions to data. If we use y equals ax to the p to fit a data set consisting of the big blue data points, we might have to adjust p. We might have to find the p that works best. If we use derive, a will be determined by derive. For any p we choose, we'll get the best possible a, or very nearly the best possible a, for that data set. Now, if we have this data set and we choose p too large, we're going to get something that looks like this. This is a power function for large p. If we choose p too small, it's going to be too gradual. It's going to be concave upward. It's going to be increasing at an increasing rate, but it's going to be a little bit too gradual. To get p about right, we kind of peg the middle of the data set. So if we do fit and it comes out like this with some of the data points above, some below, that looks like it's about right. And that's how we can determine the best value of p to use for a model. Numbers 38 and 39 concern the ratios we get from various proportionalities. Now let's move over here so we can see numbers 38 and 39. If we have y equals kx to the p, as we've seen, then the ratio y2 to y1 is kx2 to the p divided by kx1 to the p. The k's divide out and we're just left with x2 over x1, x2 to the p over x1 to the p, and we can just express that as x2 over x1 raised to the p. For example, if y equals ax squared, we're going to get a2 over a1 equals x2 over x1 squared. That's an area proportionality. So the proportionality of areas is equal to the square of the ratio of two areas will be the square of the ratio of linear dimensions. A volume is kx cubed, and what we get if we do a v2 over v1 is an x2 over x1 cubed. And that just tells us that the volume ratio is the cube of the ratio of linear dimensions. Again, not going through the details, but if we have geometrically similar figures, the area is going to be proportional to the 2/3 power of the volume, so that the area ratio, and that says a2 over a2, doesn't it? That should read a2 over a1. So let's make that change, a1. Very bad looking one, but you can see what we're trying to do. a2 over a1 is going to be the 2/3 power of v2 over v1. Similarly, since v is proportional to the 3/2 power of a, then v2 over v1 is going to be the 3/2 power of the area ratio, a2 over a1.